Okay, so good morning, dear students. Okay, so here we are. This is the last course for this strange semester, okay, concerning probability and statistics. And today, okay, in line with what we have done previously in the statistical part, okay, we are going to, to propose an introduction to the test theory. Okay, so let's go. My screen here. Okay, so what is our problem? So the starting point of this course is exactly the same starting point as in the part concerning estimation. Okay, so we start from a capital N sample, x1, x capital N, okay, of a particular distribution. And we know that this distribution depends on an unknown parameter theta. Okay, so I have this parameter that is theta parameter that is unknown. Okay, and I know that my observation, okay, depend the distribution of my observations here that are supposed to be independent and identically distributed because I have a sample here. Okay, depend on this theta. So in the part concerning estimation, my idea was okay to be able to have a way in order to approximate my theta, okay, using my observations. Okay, so it's the aim of the estimation part. Okay, and we have seen that one way to do this, okay, one systematic way to do this, okay, is why not to use the maximum likelihood estimator. Okay. In the case where theta is a mean, okay, we have seen that the sample mean often arise in this kind of problem, okay? If theta is a variance, we have seen that the variance, the sample variance or the corrected sample variance arise naturally in this kind of situation, okay? But theta may be a general parameter of a distribution. So in the estimation part, we want to find an approximation of theta, let's say, okay. In the part concerning test, okay, we are going to propose rational process in order to check if the parameter theta fulfills some property or not, okay? So to be clear, in the estimation part, my aim was to obtain an approximation, okay, of theta. And to measure the quality of this approximation, okay, I have proposed several points of view, the one being the one of the mean square error, okay? I compare the estimators, okay, by their mean square errors, okay, that is equivalent to compare their variance, okay, if they are unbiased, okay? In the part concerning estimation, I have also presented a slightly different point of view, that is the construction of confidence interval. So in the construction of confidence interval, my aim, okay, is not to find a single approximation of theta, but to have a little bit more, that is to build, okay, random intervals, okay, for which I know that theta belong with a high level of probability, okay. So it's something that is a little bit more precise because you have none other an approximation, but you have also, okay, a kind of control of the error you do through the confidence interval. What we are going to do today in the test framework, okay, but is a kind of generalization of what we do for confidence interval, because you will see that the way we obtain confidence interval is in some sense, okay, a particular way to obtain, okay, some particular region of the set of the problem, okay, for which theta will belong or not, okay? So I want to test some hypotheses, okay? So let's introduce some vocabulary at the beginning, okay? So what we call the null hypothesis, okay, is in fact the hypothesis we want to test, okay? So I call it H0. It's the hypothesis of interest, and I will give you some example just after, okay? So the hypothesis of interest. You want a rational process in order to check if H0 is fulfilled or not fulfilled. Okay. Negative hypothesis, okay, is in general what happens when H0 is not fulfilled. So it's the set of alternatives to H0, and I denote this other set of hypotheses as H1. So in some sense, okay, we want to test H0 versus H1, okay? It will be my objective to test H0 versus H1, okay? We say that an hypothesis is simple if it completely specifies the model and composite otherwise. Okay, so let's do a little example concerning this, okay? So in the framework, so you are going to see that today, okay, so I won't do proofs, contrary to what I have done in the part concerning estimation, where I have done a lot of proofs. Here I will prove nothing, but I will try to present the notion through examples, okay, in particular through examples dealing with the Gaussian distribution. Okay, it's what I will do mainly today. And you will see that in the tutorial, I will also propose some examples in the discrete case, because you know that when you have a sample here, the distribution of each random variable may be a continuous one, okay, an exponential, a Gaussian, a gamma, whatever, okay, but it also can be a discrete, okay, distribution as, let's say, Poisson or Bernoulli, binomial, okay. So what I mean by a simple hypothesis in opposition with what we call a composite hypothesis, so it's just the following. So let's take an example to be clear with this. So suppose that, okay, my theta here is equal to mu. And mu is the mean of a Gaussian with variance 1, okay? So I may have, okay, several hypotheses that I want to test. So for example, okay, the simplest one is to test, okay, so for H0, I can take, for example, the fact that theta is equal to a particular theta 0. I can test the fact that, okay, let's say, for example, theta is equal to 0. Is the mean equal to 0? It's what I want to test, okay? And I can test it against, so it will be the first example we are going to do after, with respect to theta equal to another value, okay? So you have a small theta here, theta 1, theta 2, okay? So here we have simple hypothesis, and also a simple hypothesis here. Why I have this? Because if I give you that theta is equal to theta 0, you have mu, and so you have completely, okay, the distribution of your random variable. It means that if you know the hypothesis, it will completely specify, okay, the distribution you are going to deal with. Exactly as if I give you theta equal to theta 1, okay, it's also a simple hypothesis because, okay, if you have the mean of the Gaussian, you have everything knowing that the variance is equal to 1, okay? So another example, maybe this one. I can test, once again, if theta is equal to theta 0 against, in fact, here, so not theta equal to another value, but just theta different from theta 0, okay? So here you have an hypothesis that is simple. And here you have an hypothesis that is a composite hypothesis because, okay, the only thing you know is that theta is not theta 0, something that is not sufficient to know the particular value of your parameter theta, okay? So I can give a third example if I want, okay? So I can test, for example, I don't know, theta strictly greater than theta 0 against theta less than theta 0. You want to check if you are strictly greater than a particular mean, okay, or not. And here in this situation, okay, you have something that is composite here and also composite. Okay. And what we are going to call a statistical test, it will be a procedure, okay, to discern whether or not H0 is rejected. Okay, so in test, we want to find rational process in order to be able to deduce if we can say that my initial hypothesis, my new hypothesis H0 is fulfilled or not, that is rejected or not. Okay, so just a little question of vocabulary here. So in general, okay, when we deal with test, okay, the contrary to rejection is not what we call acceptance, because acceptance is something that is really strong. It's something that is, let's say, related to the truth. So in general, okay, an hypothesis may be rejected or not rejected simply, okay, with the fact that not rejected, okay, doesn't really mean for us the acceptance, because we have in mind that we are going to do statistics, that is things that are in relation with probability. And so we will take decision with a certain level of probability that is not one, okay, something that is a little bit less than one. So we don't do deterministic process in order to check whether or not H0 is rejected or not, okay, but we do, okay, things in relation with probability, okay. So that's why, okay, in general, if you don't reject H0, you say that you not accept H0, you don't say that you accept H0, okay. So it's just a little point of vocabulary. Okay, so let's enter in a little bit more details, okay. How we are going to build this statistical rational process in order to check if my hypothesis H0 is fulfilled or not, that is rejected or not. So we are going to build this process on my observations, okay? So my observations that are x1, x2. And in fact, the way we are going to use them, okay, is building what I have already called, okay, in previous parts, okay, statistics. And what is a statistic, okay, or an estimator, okay, it's an equivalent definition. It's just something that I denote by C of capital X. And for me, C of capital X will be just a mapping depending on my capital N observations. Okay, so for example, we have already seen statistics together. You may have, for example, that C of X is equal to the sample mean. I have here a regular mapping of the observation, but you can also take, okay, why not, depending on the problem, C of X that is equal to the corrected sample variance, okay, or something that is just, okay, so this definition is very general, okay, it's just a mapping, okay, depending on my observations, okay? And by regular, I just mean that, okay, it has to fulfill some classical hypothesis, but that I don't enter into the details here because in general, we are going to deal more or less with polynomials in the observations, okay? And in fact, how we are going to build our rational process, okay, the idea is to take decision, okay, to reject or not my hypothesis H0, depending on the value of these statistics. Okay, depending on the value of these statistics, I will reject or not my H0. And what we call a critical region or a region of rejection, this is the values of the statistics for which I will reject my null hypothesis H0. And I denote this region by R, capital RC, okay, that is my rejection region or my critical region. So R for region, C for critical, okay? And what I will do is that if this number belongs to this one, it means that I will reject my hypothesis. If this is not the case, is C of X doesn't belong to this region, okay, I won't reject my hypothesis, okay? That's why by abuse of vocabulary, okay, and contrary just what I have said previously, the complementary set of this one, that is the region for which I won't reject, okay, my hypothesis, is called in the literature as the region of acceptance, okay, or I can call it, I prefer, the non-rejection region. Okay. So I repeat, I have a regular mapping depending on my observation. For example, to fix the idea at the beginning, okay, the sample mean or the corrected sample variance or the sample variance or anything you have in mind, that is just, okay, a mapping depending on my observation. Depending on the values of C of X, I will reject or not my hypothesis, okay? And I denote by RC the set of the possible values for which I will reject my H0, and so RC complementary. So here, be careful, huh? The notation are maybe a little bit strange, but RC here is just RC, the critical region complementary set. Okay, so the C here that is for critical is not the same as this one that is for complementary. Okay, so here the C here is complementary. So I am in the following situation concretely. Okay, I have in fact 4 possibilities. The first 2 are H0 is, let's say, true or false. Okay, because I know that my distribution depends on an unknown parameter. By unknown, I mean that a one that I am not able to know, but it exists a priori in the real life, okay, but I don't have access to this value. So my H0 is true or false, okay? And when I build statistics, okay, and a critical region, okay, I have 2 situations. The case where the values of my statistic belongs to the critical region or not. Okay, so I have in fact here 4 possibilities. The case where H0 is true and the set of my statistics, the values of my statistic belong to the critical region. The case where H0 is false and when I belongs to this one. The case where H0 is true and the set of my values for my statistic doesn't belong to the rejection region, and so on. And in this way, I have four possibilities. Okay, so I have 4 possibilities depending whether or not, okay, my H0 is true and whether or not Cx belongs to the critical region. So I have in fact 4 possibilities that we are going to detail a little. Okay, so I have this one. I have put some of them in green and I have put some of them in red. Okay, why? But because that if C of X belongs to RC, it means that I reject. And if I reject an hypothesis that is false, it's okay, it's perfect for me because, okay, my process is a good process in this situation because I reject something that is false. Okay, so it's in a situation here where I am okay with my process because it rejects something that is false. Equivalently, if I am in this situation, it means that I don't reject. I don't write accept, I repeat, I write just don't reject. I don't reject something that is true. This is also a nice situation because I don't reject something that is true. Okay. And then I have the 2 other possibilities. But the case where here I reject something that is true and it's not a good situation. It's what I call the type 1 error. The situation where I will reject something that is true. And in general, okay, I don't want to do this, or if I do this, okay, I want to do it with a very, very small probability. In fact, and it will be exactly what we are going to do just after. In this situation, the second bad case here is the case where I don't reject, but I don't reject something that is false. It's not a good situation for me because I don't reject something that is false. And it's what I call the type 2 error. Okay, it's what I call the type 2 error. And the idea will be, so for this situation, it's perfect. I like them, okay, because I reject something that is false. I don't reject something that is true, but I want to have some control concerning the two types of errors I can't do when I use a statistics and a critical region in order to check whether or not an hypothesis is fulfilled, here H0. From now on, okay, I will consider particular case of H0 and H1, okay? So if I come back to my previous examples here, I have given to you some example here. And you see that all these three examples may be written on the following form. Theta belongs to a particular set of parameters that I denote by capital theta 0. It's for H0. And H1, I can write it, theta belongs to another set of parameter theta 1. Okay, and typically, if I am in this situation here, I have my big theta 0 that is just, for example, here, the interval theta 0 plus infinity, because I want to be strictly greater than theta 0. And here, my big theta 1 is what? But it's minus infinity, theta 0 included. Okay, so from now on, my null hypothesis or my alternative hypothesis, so that is H0 or H1, will be of this form. So it means that I will test if theta belongs to a set theta 0, or I will against versus theta belongs to another set, with the fact that these two are disjoint. So big theta 0 intersected with big theta 1 has to be disjoint. Okay? So it's what we are going to do. Okay. So keep in mind that I have two good situations on which I have, let's say, nothing to say because I am happy to be in this situation. I reject something that is false. I don't reject something that is true. Perfect. Okay. And I have two problems. That is what I call the type 1 error, that is to reject something that is true, and the type 2 error, that is not reject something that is false. Okay. Okay, what we called the size or the level of a test is the following number. So it is alpha, the size of the test, that is the supremum over theta 0. So theta 0, okay, let's remind that H0 is theta belongs to the big theta 0 here. So it's the supremum of what? Of the probability that under theta, C of x belongs to the rejection region. So here I am in the situation where my parameter belongs to the set of parameters related to H0, and I am interested in the probability that in this situation I reject. So if I come back to the previous slide, okay, alpha is related to this type 1 error, okay? It's in fact fixing a theta in the set of parameters related with my null hypothesis H0, I compute the probability that I reject, okay? So it's the supremum over all the possible value for theta related to my hypothesis H0. It's the probability here to reject. So it's something that is related to type 1 error. So just a remark concerning this situation here. Okay, so what is the meaning of p theta? So if I want to compute this probability, since I know that my statistics depend on the observation, I need to know theta. Okay, because okay, my distribution inside depends on my unknown parameter. And what I called p theta of Cx belonging to Rc here is just p of Cx belonging to Rc when theta is fixed. Okay. So typically here, what I do, I take my capital theta 0 here, okay? And then what I do, I compute the probability of the rejection or the probability of rejecting my hypothesis under all the parameters belonging to capital theta 0, and I do the supremum. It's what I call the level of the size of the test. That is something that is related to type 1 error, okay? And in the same way, so here be careful because here you have theta 0, here you have theta 1. So these two quantities are the same here. It's the probability to reject, okay, for a parameter theta. If I consider the supremum over theta 1 and keep in mind that theta 1 is related to the alternative hypothesis, that is theta belongs to capital theta 1, okay? This quantity is exactly, okay, what we called the power of the test. And I denote this power of the test by 1 minus beta, okay? That is the supremum that theta belongs to theta 1, knowing that, okay, and the supremum over the values of theta in theta 1 of the probability to reject, okay? And what is this one? Okay, I can write it this way using complementary set. Okay, I can write it as 1 minus the supremum for theta belonging to theta 1 of what? Of p theta, but the complementary set, that is C of x doesn't belong to the rejection region, that is doesn't belong to the rejection method, that is belongs to the complementary set. And so my beta here is exactly this quantity. It is the supremum, okay, when theta belongs to the alternative hypothesis of the probability here, where I don't reject here. Okay. And so in practice, this quantity is related to the type 2 error. The 2 error I do when I am in the bad situation, okay? The one where I reject when I know that I am true. That is something in relation with this one. I know that I am true because theta belongs to theta 0, and I am interested in the probability to reject in this situation, okay? And I consider the supremum of all these probabilities. Second type of situation, I don't reject, okay? And I am false, so it's a second problem, okay? And here, the type 2 error is controlled by this quantity, that is, okay, I consider the supremum, okay, to reject when I am in H1, okay, that I can write as 1 minus the supremum I don't reject when I am in theta 1. That is, I don't reject knowing that H0 is false because theta belongs to the alternative set of hypotheses, okay? And so, in practice, what I want to do, I want to make alpha and beta small. I want to make alpha and beta small because I want, if it's possible, to minimize, okay, the type 1 error that is related to alpha and the type 2 error that is in fact related to my beta. So I want small alpha and beta. I want small alpha and beta. And so if I have a small alpha, it means that I will have a small size or a small level for the test. That will be, I will have a small type 1 error, okay? And I want beta to be big. And what is beta to be big? So beta is a probability. So it's a parameter between, it's a supremum over probability. So it's a parameter between 0 and 1. And to say that my beta will be big means that my 1 minus beta will be small. Okay, and so that 1 minus beta, okay, is, so I want a big beta. Excuse me, I said a mistake here. So I repeat, I want alpha to be small because I want a small type 1 error, okay? I want also a small type 2 error, and to say that I have a small type 2 error means that this one has, okay, so the type 2 error, so a small beta, okay, so a small type 2 error because I want that the supremum, that the probability that I don't reject knowing that I belong to the alternative sets of hypotheses, okay, I want this quantity to be small. So I want my beta to be small, and so my 1 minus beta to be big in the sense that it is near than 1, okay? So my objective, if possible, okay, is to minimize the alpha or to fix it small. I want to minimize beta, so, or fix it small, and beta, okay, is related through the definition by what we call the power, that is 1 minus beta. So I want a small size, and so that is a small alpha. I want to have a small beta, and so a big power. So that's why I said that alpha and beta, I want them small in order to minimize the type 1 and the type 2 errors, okay? That will imply to obtain small size for test or big power, okay? So what we call the mapping P here, it's a definition. What we call pi here is what we call the power function. Pi of theta is just the supremum of the probability that I reject, okay, for a fixed parameter theta. And I can see that, in fact, using this notation here, that my alpha is just what? It's the supremum for theta belonging to theta 0 of pi of theta with my notation here, because these probabilities are this one, the probability that I reject knowing that the parameter is theta, and my 1 minus beta will be the supremum of the same mapping here, but for theta belonging to capital theta 1, okay? So it's just what I call the power function, the one that is related with this probability, okay? And of course, that depends on my unknown parameter, theta. So in a perfect world, okay, it will be to obtain, okay, test with the smallest possible size, okay, and because I want to minimize my type 1 error, I don't want to reject if my hypothesis is true, okay? And secondly, I want to minimize my type 2 error. That is, okay, I want that the probability to accept knowing or not to reject, let's say, knowing that I am false, okay, I want it to be small. And so I want a small alpha and a big power. And the problem I have, okay, is that concretely it's something that I can't do. I can't do. Why I can't do? Because the type 1 and the type 2 errors, okay, are related. So you have a link, and I will show you in an example just after what can be this kind of link. I have a link between alpha and beta. So it means that if you want to minimize alpha and minimize beta at the same time, it won't be possible for you to do this, okay? Because in general, when you increase or decrease alpha, the converse happens for beta, okay? So I am in a situation where in the perfect situation, I want to minimize alpha and beta to obtain a small size and a big power for a test, okay? But in practice, it's not possible because size and power are linked, okay? So what we do concretely, it's a convention, okay? The convention is to fix the type 1 error to be small. General by small, I will say, okay, let's say 5% or 1% or something like this. And to expect, because I can't do more than expect, that the type 2 error won't be too big. That is, that my beta won't be too big, and so that my power won't be too small. Okay? So when we build a test, okay, we build a test from a statistic, building a rejection region or a critical region. It's the same vocabulary, in fact, here, in order, okay, to fix my type 1 error to be small. And then I study the power to check if my test is not that bad, okay, that is with a type 2 error that is not that big, okay? So it's what I want to do. Just a remark. So here you have more or less, okay, the theory of what you have below what we call, okay, test theory. That is, from a statistic, I build a critical region in order to reject or not, okay, my hypothesis of interest, that is H0. But if I want to do this concretely, what I have to do, I have to compute, let's say, the power function, in fact, because I want to compute these probabilities here, okay, in order to be able to fix my critical region and so on. In order to compute them, okay, so here you have something that is deterministic a priori. It's just a region of the R line, okay? And here you have a random variable. If I want to compute this probability, it means that if I know theta, I have to be able to know the distribution of this one, okay? So I need the distribution of the statistic if I want to do or to perform this computation concretely, okay? So it's what we are going to do in the following little example here. So let me add a white page. So let's see an example, the first example. So just let me check, okay, yes, the hypothesis I do on this example. So what I want to do here, I want to do a simple thing. I want to test the hypothesis H0, that is just theta equal to theta 0, okay? So here I am in the situation where my capital theta 0 here is just reduced to a singleton. Okay, my capital theta 0, that is the set for the parameters, okay, for the new hypothesis. Here it's just this singleton because I test if theta is equal to theta 0. So here you have a simple, okay, hypothesis. And I want to test it against theta equal to theta 1. So my big theta 1 is equal to the singleton theta 1. And once again here, I have a simple hypothesis. So if I want to do the things concretely, okay, I need to know what are my starting distribution. And what I will do here is to be interested with a capital N sample. So I have IID N mu 1, okay? And it's what I have done here, just to be clear. So it's not, it's N mu sigma square, okay? Why not? And my parameter of interest theta will be equal to my mean. Okay, so if I come back to my notation here, my H0 is just mu equal to mu 0. And I test it versus H1, that is mu equal to mu 1. So we are going to do the following case here. We are going to suppose hypothesis, okay, that is the one I do here. I suppose that mu1 is strictly greater than mu0. Why not? Okay, the case mu0 equal to mu1 is of course meaningless. And I will suppose, in fact, that I want to test mu0 against mu1 with a mu1 that is strictly greater than mu0. At home, do the case that is exactly the same case, mu1 strictly less than mu0. It's a little exercise to do at home to check if you have understood or not the things. Okay. So what I do? So for the moment, okay, I don't have a general process in order to build test. I will show you this in a few minutes, okay? But here, I will try to give you the intuition of what can I do. So my first case, my first situation here is that we suppose that sigma square is known. Why not? And we are going to see what. In the case where sigma square is known, and you see that here you are interested, so my sigma square is known, and you are interested in fact, the mean of a Gaussian distribution. In the course concerning sampling, and also in the course concerning estimation, we have seen that if I want to approximate mu, the best thing I can do when sigma square is known, in fact, is to do what? Is to consider the sample mean. Okay, is to consider the sample mean. The sample mean is a good estimator of mu when sigma square is known, in the sense that it is the best unbiased one. Okay, so we are going to consider the quantity that approximates my mu, that is to consider x capital N over line. Okay, and I know that this x capital N over line, okay, I know everything. I know that it is an unbiased estimator, okay. So its expectation is equal to mu here. And what is this variance? We know that this variance is given by sigma square over N, okay. So we have this. In other words, I can standardize the things this way. I can standardize the things this way in order to say that x n over line minus mu over sigma the square root of n, this one follows the n0. And keep in mind that in the part concerning estimation, and when I want to build a confidence interval, okay, I have considered this kind of quantities are, okay, what I have called a pivotal quantity. It's a random variable independent of the parameters of the model. Here you have something with mean 0 and variance 1 that doesn't depend here. So this one is independent of mu and even independent of sigma square, even if here, okay, sigma square is known. So if sigma square is known, it's not a problem to depend on sigma square. Okay, so in particular, what we have. So I have my hypothesis H0, that is mu equal to mu 0. And I know that under H0, so if H0 is fulfilled, according to what I have said previously, I know that xn over line minus mu 0 over sigma multiplied by the square root of n follows n01. Okay, so if I am under the hypothesis H0, okay, this quantity here follows the N01. And I will denote this quantity by C of X. What happens if H1 is fulfilled? Full. But if H1 is fulfilled, okay, the distribution of Cx is no more N01 because, okay, I know that the parameter mu is equal to mu1. Okay, so H0, when H0 is fulfilled, okay, it means that mu is equal to mu0. H1 is fulfilled, it means that mu is equal to mu1. Okay, so when mu is equal to mu1, I know that this is this quantity that follows N01. But if I want to make appear C of X here, I can write it in the following way. I can say that I have square root of n x n over line minus mu0 plus mu0 minus mu1 over sigma. Okay, that follows the N01. And in other words, I can say that in this situation, so here you see that you make appear C of X, square root of n xn over line minus u over sigma, and then you have a number here, and so C of X follows in this situation, a Gaussian with a variance that is equal to 1, no problem, but I just add a number, so I will obtain a mean inside and a mean that is equal to the following one. Okay, so it is mu1 minus mu0 over sigma the square root of n. Okay, so C of X follows when mu is equal to mu1 a Gaussian distribution. So under H0, this C of X follows N01. Under H1, this C of X follows also a Gaussian, but a Gaussian with a mean that is known, that is mu1 minus mu0 over sigma square root of n. Okay? So if I summarize what I have obtained, I have defined a statistic. Okay, excuse me. I have defined a statistic. This way. And I know that under H0, C of X follows the N01. And under H1, C of X follows the N. So I will give it a number here, a name. I will call it, let's say, alpha 1, where alpha is given by my previous slide. That is exactly this quantity of interest here. Okay, that is square root of n mu1 minus mu0 over sigma. And if you come back to what I have done at the beginning, okay, when I have started, okay, I have supposed that I am under this condition here. Mu1 is greater than mu0, okay? And I have said to do the opposite, okay, the contrary case, okay, at home. So under mu1 strictly greater than mu0, here I have an alpha that is strictly positive. And what is the meaning of this one? With this one, I will be able to define my confidence, my critical region. Because if I am under H0, it means that in average, my C of X is 0. Okay, so let's say around 0. Under H1, my C of X is centered around a strictly positive number. So it means that under H1, okay, C of X takes in general greater values than C of X under H0. Keep in mind that I want to reject yes, I want to find a region, that is a region for which I will reject my hypothesis H0. But you see that here under H0, let's say C of X is small. Under H1, C of X is bigger, okay? So we define the following region of acceptance. We define, okay, so the following R of C is the following. The set where C of X is in fact big. Okay, why? Because if I am in this case, it means that, let's say, C of X is bigger than a particular level. Okay, and if C of X is bigger than a particular level, since I have defined R of C as my rejection region, it means that I am in fact under H1 here, because under H1, C of X is bigger than what happened under H0. Okay, so I have a natural way here in order to define a critical region, just remarking that in one case here, under my hypothesis of interest, I am small, let's say, in average. Under the alternative hypothesis, I am big. So I will reject H0 when the statistic will be big, because when it is big, it means that we are under the other one, okay? So we define this one, okay? So if I want to build my test, okay, I said that I have to fix a level and then to see what happened for the power of the test. So keep in mind that in my situation here, so alpha is always defined as the supremum for theta belonging to capital theta 0 of P theta C of X belongs to R of C. In my particular situation here, since I have a single element in capital theta, it's the probability when mu is equal to mu 0 that here C of X is greater than K. But what is this one? I know that under H0, that is when mu is equal to mu 0, I know that this one follows the N01. So my alpha, I am able to compute alpha. If I give you a K, since I know that when I have mu 0, this one follows the N01, okay, I am able to compute this probability from tables of the Gaussian distribution. And for example, okay, so I have this one this way, and I can write it here as 1 minus the probability under mu 0 that the N01 is less than K. And here you have the distribution function of a Gaussian, something that I can know with tables, okay? So keep in mind that I want alpha to be small, okay? And I will fix it in the test process, okay? So if I take alpha is equal, so small, I will take it equal to 5%. So it implies that here, if I take alpha is equal to 5%, it means that I want to find K, so find K such that P of my N01 less than K is equal to, so I can write mu 0 here, is equal to what? So 1 minus alpha, that is 0.95, okay? And let's do the job. I take a table for the Gaussian distribution. So here you have a table for the distribution of a Gaussian. And I am checking if I I can find a case such that the distribution function is equal to 0.95, and I can do this. I have 0.90, yes, 0.95, where is it here? Somewhere. I have it here, okay, more or less here, okay. I have here 0.9495 and this one, so it would be belong these two values. And what is it? So here we have 1.6 for these two, and what are the corresponding top of the two columns? So I have, okay, I will be between this one and this one. That is, I will be between this one and this one also. So it will be 1.64 or 1.65. And I see that, okay, I can take the middle of them, for example. So I can take here, excuse me. So let's come back to my whiteboard, okay. I can take K. Okay, I can take K from the Gaussian table as 1.64.1.65, let's say, over 2. Okay, that is just 1.645. Okay, so it means that in my particular situation here, if I fixed a level for my test, I am able to find explicitly what is the critical region. My critical region now is, okay, for alpha equal to 0.05, okay, my critical region is equal to what? It's the one where C of X is greater or equal to 1.645. Okay, so I have this. What is interesting here is that you see that my critical region, okay, is independent of mu0. You don't have mu0 here, or you have it in the statistics, okay, but the distribution here is of course totally independent of mu0. So I have this. Okay, so let's just write it this way. Okay, so I have fixed the level of the test. Okay, now I am interested in the power. So I know that 1 minus beta is equal to the supremum for theta belonging to capital theta 1 of the power function. That is now the probability that I belongs to the rejection region, that is this one. Okay. In my case, I have a single element in theta 1 that is mu1, so it will be P of mu1 C of X greater than 1.645. And so I have the possibility to compute this probability explicitly here. Why? Because I know that, okay, I know that what? We know that when mu is equal to mu1, it's what I have done previously, C of X follows a n. So just a remark here concerning my notations, okay, it's not a good notation. I have white in alpha here, it's not a good idea because my alpha, okay, is something that is related to the level of the test. So just, okay, I will give it another name, okay. So instead of writing alpha, I will call it A, basically. I just use A as a notation, okay, it's a notation. So it fulfills what? It fulfills NA1, okay? So if I want to compute this, P of mu1 C of X greater than 1.645, and how to do? But if I want to use the table of a Gaussian, I can write it this way, C of X minus its mean greater than 1.645 minus A, okay? This one can be obtained from the table of a Gaussian distribution in the following way, because here now you have now this one that follows N01 when mu is equal to mu1, okay, because I have subtracted its mean. And it's the probability 1 minus the probability that my N01 is less than 1.645 minus A. And it means that from the table, okay, this one may be computed from the table of the cumulative distribution function of N01. So I can do everything explicitly here, okay? I can do everything explicitly. So if I fix a level, okay, I obtain my precise confidence critical region here, okay? My critical region. And then, okay, if I obtain it, okay, I can see what happened for the power of the test here. I compute it here, so I won't do explicitly the computation now because I have to fix, if I want to do this explicitly, I have to fix a mu1, okay, that can be, okay, particular value. I have to fix a mu0 and I have to fix a number of observation, but if I do the job, I am able to compute explicitly this quantity, okay? So in the case of testing that mu is equal to mu0 versus mu is equal to mu1 when mu1 is strictly greater than mu0, I have built here a test, and keep in mind that the initial idea to do this test was to try to say two things. To say first that in the case of Gaussian, we have seen that the sample mean is something that is really interesting in order to approximate mu. Then we see what is the distribution of the sample mean under H0 and H1, okay? And I have these two here, okay? In particular, I see that under H0, if I consider this quantity, it's a Gaussian N01, and under H1, if I consider this quantity, I have a Gaussian, but with a mean that is strictly positive. So it's the way we build a confidence or a critical region here that is, okay, the case where my statistic here will be big, because under H0, in general, it is around 0. When I am under H1, it is around a strictly positive number. So under H1, it is greater. So my rejection region will be related with the fact that C of X is big under H1. Okay, so it's exactly what I do. And then after, it's just computation, because I have to fix my level and then fix my level as I have done at the end of this page here, okay, from the table of N01. And at the end, okay, I check what is my power. And you see here that, of course, in order to fix the level K, okay, and to fix the level, you obtain a K that is given by the level. So K here is a function of alpha. And I see that when I compute the power of my test, I have inside here my K I have obtained. So you see that inside the computation of the power of the test, you have, okay, the K that was given by the level. That's here that you see that level and power are linked. So it's not possible in general for me. If I fix one, I will have the other, okay? And so I can't minimize, okay, alpha and beta at the same time, or I can't minimize the level and maximize the power at the same time, because if I fix the level, okay, I will have something that will be a byproduct for the power, okay? So just come back that I was in this case, okay, because I have supposed sigma square to be known, okay, in order to compute explicitly the things, okay? So if sigma square is known, okay, if I give you the parameter of the model, that is mu1, mu2, the number of observation and sigma, you can compute this quantity, okay, without any kind of problem, okay? So you can't do everything explicitly. So just a remark concerning the second case, but if you know your course, it will be not complicated. So if sigma square is unknown, but if sigma square is unknown, okay, I have in the course concerning sampling, in the Gaussian case, a way to do more or less the same thing, replacing, the idea is approximate sigma square by the corrected sample variance. So the statistics of interest here will be, so keep in mind that the statistic of interest in the case sigma square known was xn over line minus mu 0 multiplied by the square root of capital N, and I have divided by sigma. Okay, but here I don't know sigma, and what I will do, I will replace sigma by the square root of the corrected sample variance. I do this. And what is interesting is that in the case where sigma square was known, if I put a sigma here, I know that C of X follows the Gaussian. In this case, when sigma square is unknown, if I replace sigma by the square root of the corrected sample variance, I know from the course, from the sampling course here, I know that you fulfill here a student distribution. So it means that all what I have done previously using Gaussian tables may be done in the case where sigma square is unknown, okay, using just table of the student distribution. Okay. So you can say the following, okay, you show us an example, okay, but okay, the argument you give, okay, was this argument with the fact that under H0, this statistic is small, under H1, this statistic is big, okay, but if I had to do this in practice by myself as a student, okay, I am not sure that I will be able to think about all these things, okay? And that's why we are going to see now, okay, a systematical process in order to do what I have done before. That is a systematical way to build a test, okay, that is called the likelihood ratio test. So I will just do a little 5-minute break in order to have a coffee, and I come back. Okay, you will see nothing in the video, but I come back in 5 minutes.